Hello everyone. So we're on page 22, okay? Page 22. And we're going to talk about reaction mechanisms. Okay, so follow along, take notes. Let's dive into this. We have reaction mechanisms, and what reaction mechanisms are, they are individual steps of a chemical reaction. So it turns out so often these chemical reactions that you have seen, that we've used over and over and over again, it actually turns out that very rarely do these things in one step turn into those things, and it usually happens in a series of steps. So for this one, what actually happens is that two nitrogen monoxides run into each other and make this like nitrogen peroxide, N2O2, and then the N2O2 will react with a free-floating oxygen molecule, and they collide, and then that produces two nitrogen dioxides. That this is the actual steps that occur to make the products, but we just show it in one step instead of two. And so the way this is going to work, this first topic, 5.4, is all about just putting these together, and I think this is really simple. You look at the steps, and if anything shows up on both the reactant and the product side, it's called an intermediate. Well, I should clarify. If it's produced in one step and consumed in a later step, it's called an intermediate, and we cancel that, and then anything that's left over we bring down. So the two nitrogen monoxides stay on the reactant side, the O2 stays on the reactant side, and then two nitrogen dioxides would go on the product side. Okay, so let's do an example together. This reaction has two steps in it, step 1, step 2, and we're going to see what the overall is. And so I'm looking at this, and I go, all right, this S2O8, it's not showing up over here, so that one's not going to cancel. Oh, but this one is. Do you see how we have the two iron ions? That's going to cancel right there. And let's see if anything else cancels. Oh, this does. We had iron 2, and then we have an iron 3, right? The 3 plus. That was a product, and then it was a reactant here, and so that cancels. The overall is whatever's left over. So this would be S2O8 2 minus plus 2 iodine ions results in 2 sulfate ions, minus, plus 1 iodine molecule. Okay, so that is what we're left with overall. Okay, as I told you, an intermediate, it's produced in an earlier step and consumed in a later step. All right, let's write it down. Produced in an earlier step. Produced in an earlier step and consumed in an earlier step and consumed in a later step. Okay, so what is the intermediate? In step 1, we produced iron 3 ions, and then we consumed those iron 3 ions in a later step. This is the intermediate. So for the reaction above, the intermediate was the iron 3 plus. That's an example. For example, iron 3 plus in this one. A catalyst. We know that catalysts facilitate reactions. They lower the activation energy. The other important thing about a catalyst is that it's not part of the overall chemical reaction. It's there in the beginning and it's there in the end, and so that's why it cancels, and that's why it's not part of the overall. So a catalyst is there in the beginning and there in the end. There in the beginning and it's present, it's there in the end. If you want to sound all sciencey and fancier, instead of saying there, we could say present. It's present in the beginning and it's present in the end. So let's look at this. The iron 3 was an intermediate. It was produced in an earlier step and consumed in a later step, but the iron 2 is actually the catalyst. Do you see it in step 1? It was there in the beginning, and it was there in the end. It was a product after the final step. So when it's there in the beginning and there in the end, it cancels, and it's a catalyst. So our example of our catalyst is the iron 2+, not 3+. Iron 2+ is the catalyst. Okay, important thing. Intermediates cannot be part of the overall rate law, but catalysts can be part of the overall rate law. Let's scoot this down because we don't have a ton of room here, so I'm just going to put some bullet points on the bottom of this page. So, intermediates cannot, okay, they cannot be part of the overall rate law. Okay, intermediates cannot be part of the overall rate law. Catalysts, on the other hand, can. So catalysts can be part of the overall rate law. Okay, catalysts can be part of the overall rate law. All right, here's another cool thing. When we were doing rate laws, and let's write this down. Here's my overall reaction. And remember how reactants are the only items that we're putting concentrations we're talking about in a rate law. So if I was going to set up this rate law for that overall reaction, I would have rate is equal to K, concentration of S2O8, 2 minus, and then concentration of iodine minus. And I don't know what these are raised to. Like, remember, it's like an M and an N. So if this is 0, it's not part of it. If it's a 1, I'd write it like this. If it was a 2, I'd put a squared there. And we had experimental evidence to figure out what the orders were. That's when we were saying, in trials 1 and 2, the concentration of this doubled while that stayed constant, and the rate doubled, so this is first order. So we're looking at experimental evidence. Now, what's really cool about this is that for individual steps, for individual mechanisms, you can write the rate law of these individual mechanisms, and you don't need experimental evidence to do it. But this only works for individual steps. It doesn't work for the overall. So if I were to look at step 1 and write a rate law for this, I'm going to set up, I'm going to have my rate is equal to K, and I'm going to put a little subscript of 1 because it's step 1, just to help me keep my different rate constants in check and keep track of them. And then there was 2 reactants for step 1. We had S2O8, 2 minus, and then we also had 2 Fe, oh sorry, not 2. We'd had Fe2+. Those were the 2 reactants that were here, okay? And so what you do for individual steps is you look at the coefficients in the balanced chemical equations. So there's technically a coefficient of a 1 right here. And so when you take those coefficients and you make them the orders. So this is technically raised to the first. And then there's a 2 here, and so that one would be a second order reactant. Okay? So that is the rate law for the first step. Now, let's do the rate law for the second step. Rate is equal to K2. So this is rate constant for the second step. We have got 2 reactants again. We got iron 3+ and iodine minus. So concentration of iron 3+ and iodine minus. Okay, now let's look at those coefficients. So iron 3+ has a coefficient of 2, and so does the I minus. So this is going to be a second order, and this one's also second order. Now, how do we go about taking the rates of the individual steps and the rate laws of the individual steps and figuring out what the rate law is of the overall reaction? Because remember, we don't know what this is. It's M and N. Like, we don't know what they are raised to. And so it's really cool. You don't need to turn the page. Let me just show you something. On the AP Chem test, they will tell you if mechanisms are slow or fast. And the slow step is always the rate determining step. And so whenever we have a rate law, whatever the rate law is for the slow step, it is also the rate law for the overall reaction. So this is really interesting. And they have to tell you which steps are slow and which ones are fast. And so just from prior knowledge, and again, you wouldn't have to recognize this. They would have to tell you this on the AP Chem test. The bottom one down here, this is a fast step. And the top one, this is a slow step. Okay? So if we have 2 steps, this is the slowest of those steps. That is the rate determining step. So that means that the rate law for the overall reaction is this. Now, a couple interesting things. First off, based on this, we know that M is 1. The other thing that we know, this is iron, not the iodine minus. So if M is 1, the N is actually 0. This is going to be 1. That's going to be 0, because anything raised to 0 is 1. That's why it's not present in here. And then it is okay for catalysts to be added to a rate law. Not intermediates, but catalysts. Because when we add a catalyst, that's going to impact the rate, right? It's going to make the rate increase. And so that's why it's okay to have catalysts as part of this overall rate law. So we have, let's do final answer. So our final answer, what is the rate of the overall reaction? Well, its rate is equal to K. And usually at this point, we drop the subscript 1. It is the same. It's the same K value, but we usually drop it at that point. And then we have S2O8, 2 minus, and it's to the first, so it's first order, and then iodine is 0 order, so I don't have it in here. And then we have a catalyst as well, iron 2+, and it's got a big impact. It's second order. So that is the rate law of this overall reaction. Okay. I think we should do one more like this. Let's see, like example. Yeah. Okay, so we're gonna do another one of these. I was gonna save it, that's okay. We're going to skip page 24. We're going to do page 24 in class. I have a really cool example of why the slow step is the rate determining step, and I'll show you that in class. Let's go on to page 25. Okay, so let's see what the overall reaction is for this. Hydrogen peroxide, and it's not showing up on the product side. Okay, so that doesn't cancel. Oh, iodine. Do you see how iodine was there in the beginning on the reactant side? It was there in the end. It was, yes, it was there in the beginning. It was there in the end. So that's a catalyst. It's not part of our overall reaction, but it could be part of our overall rate law. And then this one, iodine oxygen minus, it was made in an earlier step and consumed in a later step. So this one also cancels. This is an intermediate. Okay, so that's an intermediate, and it cannot be part of our rate law, our overall rate law. So does anything else cancel? No. The hydrogen peroxides don't cancel because they're both on the reactant side, and the waters don't cancel because they're both on the product side. Okay, so we have sorry, I just want to check this really quick. We're missing one. 1, 2, 3, and there's only 1 there. Oh no, there's an O2 right here that I wasn't seeing. Okay, sorry guys. I saw H2O2 and I didn't catch this O2 product right there, and so I thought it was turning into water. I'm like, that's not balanced. Like, we don't have the right amount of oxygen, but we're doing okay. So we have 2H2O2 aqueous, right? I'm adding those together. Everything else canceled on the reactant side, so that turns into 2 water molecules, liquid, and an O2 gas. Great, so that's my overall. Now, the rate law, okay, the rate law for the overall rate law is equal to the rate law of the slow step, okay? So, since this is the slow step, what this rate law has to equal rate K2, and if we H2O2 IO minus. They are both first order because there's coefficients of 1 in front of them. But we've run into a problem, and the problem is that this rate law, we're saying that this rate law contains an intermediate. IO minus aqueous. Oh, not okay. Overall rate laws can't have an intermediate, okay? And so, what do you do if you have an intermediate? It involves a reversible reaction, okay? So, this one, we're going to come back to this. I want to show you how we actually are going to come back to an earlier step, and we're going to be dealing with a reversible reaction. Okay? So, let's look at this. We're going to run into the exact same problem here, and we're going to see how to solve it. Nitrogen trioxide is an intermediate. And we can't have that be part of the overall rate law. We do not have a catalyst on this one. That's the only one that cancels. So my overall is nitrogen monoxide gas plus, oh, and there's 2 of them, because see both of them on the reactant side. So 2 nitrogen monoxides plus O2 gas will turn into 2 nitrogen dioxide gas. Okay, so the rate law of the slow step. Okay, so for step 2, rate is equal to K, concentration of nitrogen trioxide, concentration of nitrogen monoxide. And I put them raised to the 1 because there's coefficients of 1 in front of there. And so we go, okay, great. Isn't this is the slow step, this is the rate of the slow step, so isn't this the overall rate law? And we go, this doesn't work, just like before. This doesn't work because nitrogen trioxide is an intermediate. And so when you run into this problem, here's what you're going to do. You're going to go up to the step that is a reversible step, that we have both forward reactions and reverse reactions. And I want to show you how the rate, I'm going to do step 1. Step 1. Let's do the rate of the forward reaction first. Rate of the forward reaction. And this would be K1, let's call it forward, 1 forward. And actually, let me think. Same. Yeah. So K1, it will be concentration of nitrogen monoxide O2, like that. Okay. Now, that's the forward reaction. That is where these guys are the reactants and then they're turning into this product. A reverse reaction is the opposite, where this is actually the reactant and those are the products. So I'm going to now write a rate law for this reverse reaction. So that was rate of the forward, and now I'm going to do rate of the reverse. Okay. Rate of the reverse. K nitrogen trioxide. All right. Now, what I'm going to need to double check on, so I'm going to double check this. I can't remember if these K's are the same or if they're different. It's the same reaction, but it's going the opposite direction. So let me do some checking on that, and I'll give you that answer in class. For now, we'll just assume that they're different. So it's like this will be one of the forward reaction. This will be one of the reverse reaction. All right. So whenever you have a reversible reaction, the rate of the forward reaction is always equal to the rate of the reverse reaction. And so the rate of the forward is going to equal the rate of the reverse. So I could say like K1 forward, concentration of nitrogen monoxide, concentration of oxygen O2, that's going to equal K1 of the reverse reaction, nitrogen, concentration of nitrogen trioxide. And our issue right now is this intermediate. So I'm going to just divide that K over, so then it'll be like, oh, and actually, for simplicity's sake, how about we just do this? Okay. So we have this fraction of like K1 forward divided by K2 reverse, and that's multiplied by those concentrations. That's the same as the concentration of this dude right here, the nitrogen trioxide. And so if I go to my slow step, the rate law of my slow step, that's my intermediate, that's the issue. This is fine. So I'm going to take what it solves for, and I'm going to plug it in there. Okay. So it's going to be K2, K1 forward divided by K1 reverse, and then instead of this nitrogen trioxide, it's concentration of NO times by O2. And then this guy doesn't disappear, and often students miss that because these two together replaced this nitrogen trioxide, and then that one didn't disappear. Okay. Simplify it a little bit. Here's going to be my final answer. Rate is equal to K. All right, so I'm going to take all of these K's, they multiply and divide, and I'm just going to, it turns into a new K. So it's like, it just all becomes whatever this K is. And then I had nitrogen monoxide, but there's two of them and they're multiplied together, so it's just like second order. Nitrogen monoxide squared, and then O2 first order. And that is the overall rate law for this reaction. Okay. If the slow step does not contain an intermediate, then you're good, you're done. If the slow step does contain an intermediate, then you have to figure out for a reversible reaction what the rate of the forward and the rate law of the reverse, and you set them equal to each other, because in every single reversible reaction, the rate of the forward reaction is equal to the rate of the reverse. You solve for the intermediate, and then you take what it equals and you plug it in, and that's going to be your final answer, your rate law there. All right, let's do one last one, and then we'll be done. Okay. So, oh, this is exactly the same as the last one. We're not doing it again. Okay, this is exactly the same as the last one. So we're not going to do that one again. How about we go back to that one that we didn't wrap up, and let's call the first one reversible. Okay, so I'm on page 25. Page 25, I'm going back to the top here, and I said, wait, I'm running into a problem because here's my slow step, and I did the rate law for the slow step, and I see that it has an intermediate. So I can't be done because I have an intermediate. If I didn't have an intermediate, I'd be done. That's my answer. So will you add a little arrowhead here? We're going to say that this is a reversible reaction. And if this is a reversible reaction, the rate of the forward reaction is going to equal the rate of the reverse reaction. So let's do the rate of the forward reaction. Rate is equal to K1 forward concentration of H2O2 concentration of iodine minus. So that's the first one, and they're ones because there's coefficients of 1, and it's going to equal the rate of the reverse, which is K1 reverse. And then we got water and this intermediate. Okay, water and that intermediate. And so going that way, they're both coefficients of 1. So IO minus and water. Okay, we need to solve for the intermediate because that's my problem right now. So I'm going to divide by K and I'm going to divide by water. And so what we're going to get is K1 forward divided by K1 reverse, and I'm separate. It'll make sense more in just a moment why I'm like separating that. And then we're gonna have H2O2 and iodine minus divided by water, and this whole thing equals this intermediate. So now instead of writing this in, I'm going to take this and I'm going to plug it in for that. And when I do that, here's what happens. The second step. All of the K's will combine, so we will have K2, K1 forward divided by K1 reverse. This one's still going to be there, and it's going to be multiplied by all of this. So how about I put these ones together? So we're going to have concentration of H2O2 second order. Then we're going to have the iodine, I minus, and that's going to be divided by the water. That's there. Okay, well, we'll practice this more in class, and we'll answer any questions that you guys have on this. Okay. Alrighty, everyone, I will see you in class. Thank you for taking the time to watch the video. Good work.